welcome once again to our classes. So, we will continue our discussion on the post-metallocene catalyst for olefin polymerizations, and we will cover the concept like non-metallocene catalysts at this designing and chemical structure and its polymerization activity, and obviously the advantage over the other metallocene catalyst and Ziegler-Natta catalysts. Okay. So, in the last class we discussed or started our discussion on the constant geometry catalyst, that is the very successful the general structure of this one. You will see that Cp, this may be different simple Cp or substituted Cp, okay, and this X is the donor, that may be nitrogen, phosphorus or oxygen based donors, and the bridging units may be the boron, phosphorus, carbon, okay, or nitrogen or silicon, but however the bridging unit should be smaller, so that the openingness on this side is more, okay, is more, and that's why it is perfect for the high molecular weight polyethylene or the copolymerization of the ethylene and with the other copolymer, as example like longer alkenes, alpha alkenes, okay. So, perfect for other alpha alkenes, not only the just ethylene, okay. And you will see that due to the advantageous properties, okay, is improved catalytic activity. The molecular weight is very huge, you can get the ultra high molecular weight, but the only problem is that the stereoregularity is less than the metallocene based catalyst, chiral metallocene based catalyst, okay. As example, if you for the chiral metallocene, it is, you can go more than 0.9, but in this case, okay, the CGC type catalyst, you will be maximum you can get like 0.7. That means you have to sacrifice, although the reactivity or the activity is much higher than the other catalysts, okay. So, but that what are the advantage here? You see that is a high catalytic activity, okay. Generally the activity of the catalyst is expressed in as the kg of the polymer per kilogram metal per hour, okay. So, that is the expression for the catalytic efficiency of a catalyst. So, you will see that this is in the order of 10 to the 6, that is quite huge, okay. High alpha olefin comonomer incorporation, that I told that if it can coordinate nicely with the longer alpha alkenes, as example hexene, butene, octene or even the styrene, okay. Thermal stability is much higher than the other metallocenes, and perfect for the linear low density polyethylenes because it can nicely copolymerize with other alpha olefins. So, that are the quite advantageous, and that's why the industry has accepted. This is the one of the very famous and catalyst, that is the Dow's CGC catalyst, and Dow Chemicals basically first discovered or commercialized this catalyst. And here you will see that this was around 1990 it was first reported with this high efficiency, and mechanism is very much similar as the other metallocene based catalyst. Here you will see that this again you have to use a co-initiator, either the MAU or the phosphine based, okay. So, whatever is the preferred, we can use it, there is no limitation on that one. So, here you will see that this MAU has a dual role, and it will give, after the alkylation and the abstraction of the methyl group, you will get this, the active species with the titanium and with positive charge, and that X or the methyl is abstracted by the MAU. Okay, and then C2H4, that is the ethylene is coordinate. So this is basically the coordination of pi coordination of alkene. Okay, and then after that it is undergoing the insertion reaction. So this is basically the insertion reactions, and then the following through multiple steps you will get the multiple propagation, and you will get basically the propagation of the polymer chain. Okay, and you will get this polymer. Okay, so mechanism is same as we have seen for the other metallocene based catalysts. Okay, so there is no difference on it. Okay, so after that successful discovery of the Dow's CGC catalyst, high molecular weight, exceptionally high molecular weight, but the problem is the stereoregularity. So many research groups had tried to develop different CGC type of catalysts in time, and you see some of the examples. This is basically just for information. Okay, nothing like okay, this is just for information that how different type of ligands, different type of donors are possible. Here you see that this is basically the bridging is a cyclic bridge. Okay, and here you will see that again the donor is again the amino, and here you will see that this is again the amino. So all are the main structural feature is same. So only the bridging moiety or the CP bridging CP units have been modified to induce the chirality or to induce the electronic factor, which will be feasible for the polymerizations. So there are vast scope on this kind of catalyst for the development of the new catalyst of the CGC category of the catalyst. So mainly this chemistry is dominated by the titanium, okay, metals, titanium 4. So now the recent progress of in this chemistry, and the post-metallocene based chemistry is the non-metallocene catalyst. You know that CP based ligands are expensive, okay, especially if you try with the substituted CP is quite expensive, like for this kind of ligands, you see this is quite expensive. So simple ligands are always desirable. It is economic, okay, so cost effective, and if the activity is good enough, then industry people will love it, will accept it very easily, because it will be more economic. So in that way, the category of the non-metallocene catalysts started to develop. These are basically quite new. They all started around 2010 or so, like that. And you will see that here no metallocene, so no metallocene based catalyst, so no CP rings, okay, here no cyclopentadiene rings, okay, and all are actually titanium, zirconium, hafnium, that is the group 4 transition metal. So that means the reactivity and the polymerization mechanism will be very much similar the way we have seen for the CGC or the metallocene based catalyst. And ligands are either the phenoxyimine, okay, that is you will see that that is the phenoxyimine, okay, or the pyrrolidinoimine, okay, that is the pyrrolidinoimine, okay, or the phenoxyether. So here you will see this is the phenoxyether. So either phenoxyether or the pyrrolidinoimine or the phenoxyimine. So those are the chelating ligands. I am sure you know that what is the chelating. So chelating is basically multidentate ligands and entropically favored complexes. So you can make the chelate complex very easily using the suitable chelating ligands. So here you will see that again the basic structure is same. So these are the active sites. Okay, so these are the active sites in all the cases, and these are basically the ligands by the different type of pyrrolidino, phenoxyamine or phenoxyether. Okay, and this kind of catalysts have also show that good and in some cases high activity towards olefin polymerations. There is some advantage, disadvantage, but these catalysts are very cost effective, okay, very economic, because there is not much really expensive ligands in this one. You can easily prepare by condensation reactions. Okay, so here one of the very famous, okay, the ligand, the complex system is the phenoxyamine. Okay, so this is actually the in English is called the phenoxyamine, but in Japanese is called phenoxyamine. So that's why it is called as Fi. So related ligands are like a this one pyrrolidinoimine. Okay, so this is, you will see, this is the pyrrolidinoimine. So this is the another category of the catalyst, and this is, you will see, phenoxyether. So this is my phenoxyether. Okay, so this is called the Fe type catalyst, and here you will see that indolidamine. So this is the indole. Okay, so this is the indolide imine. So this is called the II. Okay, and apart from this four category, this phenoxyamine is quite popular and gives the good activity. Okay, so here see in the these catalysts are non-symmetric. Okay, and heteroatom the donors are there, nitrogen, oxygen. So you will give a different type of isomers. Okay, the regioisomers and also the stereoisomers, and these are also the flexible, electronically flexible. That means it can accommodate the even the sterically hindered monomers. Okay, so that means it easily can coordinate the different type of the monomers, the alkene monomers. So that is three criteria are very important. Okay, non-centrosymmetric, heteroatom content, and electronically flexible. Okay, so here let's this one you have to, like this, you check the phenoxyamine. So let's take this category of the ligand first and try to understand that why what kind of isomers are possible in solution. Okay, so these are all the homogeneous catalysts. So here you will see NO is basically the phenoxyamine. Okay, so this is basically NO in cartoon we have seen. So this is the phenoxyamine. Okay, phenoxyamine. Okay, now here you will see that this is possible one isomer, that is oxygen and oxygen trans. Here nitrogen and oxygen trans. So here the two chlorides are cis, here also cis, here also cis. Okay, and this case it is trans and it is trans. Okay, but think over it, how the reaction mechanism, the polymerization happens. There will be alkene coordination and then the insertion. So that means this will be not effective, this will be not effective for the polymerization. So I am interested for this one, or this one. It has been observed by spectroscopic method and also by crystal structure that this isomer is the predominant. So this is the predominant structure. Okay, and active sites are cis, that is the matching. And why you need the active sites are cis? Because you have to have the, if you recall the polymerization mechanism, so you have to have the, okay, like that one. So this is using the co-catalyst, okay, as example like MAO. Okay, so what you have to get, you have to you have to create a vacant site, and this one is, let's say, methyl. Okay, and your alkene will coordinate here. So if you have a, let's say, this one, so this will coordinate here, and then it will undergo the polymerization. Okay. So cis positions, the two chlorides, the cis isomer is essential for the polymerizations. Okay, fine. So here you will see that lots of catalysts have been developed time to time, and some of the data I will try to give. This is especially for the industrial personnel, that to understand how these catalysts are effective in polymerizations. So here you will see that this phenoxyamine type of catalyst here, this catalyst, let's say this is the 6552 or kg polyethylene per mole of catalyst per hour. Okay, and this one you will see that this is 1.02 in 10 to the 7, that is the activity. Okay, so this is basically the activity, and you will get the very high molecular weight, that is the ultra high molecular weight polyethylene, and activity in the range of 1.02 in 10 to the 7, and this one is quite moderate, 10 to the 6. That means you will see that this catalyst and this catalyst is very effective for the very high molecular weight, and it is called ultra high molecular weight polyethylene. Okay, so this is really effective. Okay, and for the polyethylene, so high, if you want targeting for the high molecular weight polyethylene, these are the catalysts are suitable and perfect. Okay, so here also see that different type of catalysts have been developed, and you see that how the different substituents varies the activity. Okay, so this is just for information and to see that what are the effects of the substituents and how we can tune the electronic property and also can tune its reactivity. Okay, so these are really very interesting, and not only that one, you can also control the tacticity by to some extent by changing this R group. Okay, you have a three option, R1, R2 and R3. So depending on the different and inducing the asymmetry and or inducing the or installing the different substituents, you can also get the atactic, syndotactic or isotactic polypropylene if you use the propylene as a monomer. So highly active, and also you can get the tacticity in the polymer. So you are fulfilling both the criteria. Okay, with the cheaper, comparatively cheaper catalyst. So that is perfect. Okay, and another category and is the alpha diimine chelates of late transition metals. Okay, so first transition, that is that early transition metals, as example zirconium, titanium, all these are oxophilic, that is not really compatible with polar monomers, or as example acrylic monomers. Okay, acrylate monomers. But for if you use the late transition metals, as example nickel, palladium, those are less oxophilic, that means compatible with polar monomers. So if we can make the similar catalyst, okay, with my late transition metals, as example nickel, palladium, etc., then this will be much more compatible with my polar monomers, so that we can make the block copolymers, or we can make the amphiphilic polymers, where there will be the non-polar part and also the polar part, non-polar block and polar block, using the polar and non-polar monomers. So that will be very nice if we can make this kind of catalyst. Okay, so here you will see that this is the alpha diimine chelate complexes, and here it is nickel. Okay, and this kind of ligands are very easily prepared by simple condensation, Schiff-based type of condensation reactions. Okay, and not only that one, this also, like here you will see this is the phosphine. Okay, and this is the alkoxy kind of chelate ligands are also been developed and reported. Okay, so bulky alpha diimine ligands favors monomer insertion over beta hydride transformation. So here this one, if you put the R group quite bulky, it actually favors the insertion reactions than the beta hydride transfer. So that is you have to keep in mind while designing new ligands or the selecting the ligands from a library. Okay, However, steric bulk in R or ortho position here, okay, see what will happen, that molecular weight decreases because you are putting the steric hindrance in this side. So this side has to be open, okay, otherwise we should not put any other steric hindrance group here in this one. So that should be like a simple phenyl or maybe the para substituted, not the ortho substituted. Then there will be less activity of these polymers. However, these alpha diamine chelate complexes have now very popular and very effective, and many industries are also accepting these polymers, these catalysts for polymer synthesis. The mechanism is very simple. Okay, here you will see that MAU is again activating the catalyst. So, and then you would see here that after activating, this is the active species, okay, active catalytic site, and then ethylene is coordinating, okay. So, and then it is insertion reactions again. So, ethylene coordination and insertion as it happened in the previous catalysts, and then the way it is actually propagating. P means polymer, so it's now like that propagation, okay. So multiple steps and the propagation like that, okay. So this kind of polymers catalyst are very effective. You can get the molecular weight of around 10 to the 6 molecular weight, that is Dalton, okay. That is quite good, and not only that, you can get considerable branching. So as you know that we also sometimes purposively put the branching in the polyethylene to induce different properties and for getting a particular applications. So like for like linear polyethylene, this is the linear polyethylene, and if you need a quite good branching, this okay kind of catalyst will be perfect, because you will see that it can induce the considerable branching. Branching is like, see, okay, this one 100 per 1000 of ethylene units, or for the palladium, and for nickel it is up to 50 per 1000 ethylene moieties, okay. So how this branching happens, that is really very interesting. I will show you, okay. So what is the how the branching happens? This is actually by chain walking mechanism. I will give a very cartoon diagram first to understand. So in first I will discuss that what is the normal, okay, cases. So like you see, this is the metal center, okay, and if I have now monomer, so what will happen? It will, okay, it will just increase in the length. So this is my active side, okay, that is the metal active catalyst active side, okay. And now if I put another monomer, then what will happen? So it will like that. So it will longer. So it will be longer and longer. Now in case of chain walking, okay, what is possible? Very interesting. So this is my polymer with active catalytic site. Now chain walking, what will happen? So there will be this active site is now here like this one. So it's basically active site is moved. How it is moved, I will show you, okay. Now first you see the pathway, okay, what are the chain walking. Now if we have a monomer, so what will happen? So this is like that, okay. So now I have now another monomer, okay. Now what will happen? Now this one is the longer, okay. So this monomer inserted here. Now this has become longer, okay. Now again the chain walking, let's say first chain walking. Now what will happen here? So here and now here. Now again, okay, what will happen? Now you will see that okay, so this is now my active site, this one. Okay, so this is now my active site. So similarly it will go again the chain walking, and you will see basically the branching here, branching here, branching. Okay, you will see. Now this is the cartoon diagram. How it is possible? By chemistry, by bond breaking and bond making, you will understand here. So here you will see that this is my beta H, okay, and undergoing the beta hydride elimination. So what is happening? So this is, you will getting the alkene here again, and this is the hydride you are getting by beta hydride elimination, and then there is a bond rotation. Okay, so here you will see that what happens, this one is basically rotated, this alkene bond. Okay, then this is the bond rotation step. Now due to the bond rotation, okay, hydrogen now has been retransferred. Okay, so here what is happening, you see that this hydrogen now has, the alkene has been inserted, and now you have a metal carbon single bond, metal carbon sigma bond, okay, and this is the metal carbon pi bond. Now due to this rotation, what will happen? Now this methyl group, okay, you will see this methyl group, this one is now here, okay, and now this hydride, this beta hydride is now interacting with the metal like the agostic interaction. Okay, and this will repeat. So now after repetition, see, you are here, we will getting the branching here. Okay, so what are the steps mechanistically? So this is the beta hydride elimination and the bond rotation. Okay, by through the single, and then the another beta H is coming in close proximity to the metal center, and then again it's forming the metal hydride, and then again the insertion, again the rotation. In that way you will getting the chain walking, and you will get the hyper branching. Sometimes is a branching is quite considerable amount. Okay, similarly the other catalyst, very famous catalyst, that is the Brookhart catalyst. This is actually palladium based, and again it's a imine based, okay, diimine based. Okay, so this is, you will see that again the imine are ligands are, donors are there, and this is very good because this is compatible with the monomer with the oxygen atoms, as example like acrylic type of monomers, and you can make block copolymers. You see here, perfect for the block copolymerization for polar and non-polar monomer. Okay, so this is the another breakthrough in the non-metallocene based catalyst. Okay, so it's a result in highly branched polymer with ester groups located at the end, that is the chain walking. You are getting the amphiphilic copolymers, sometimes you need for different purpose, and is a highly compatible with versatile number of the olefin monomers. Okay, so not only for the olefin, alkyl olefin, it also like a styrene, acrylic monomers, and various. Okay, so in conclusion, what we have learned today, we are basically learned that the development of olefin polymerization catalyst from metallocene to post-metallocene. Okay, and we learned the design, structural property and exceptionally high activity, okay, and definitely the cost effective. Okay. We also learned the mechanism and the strategy. Okay. So, here we are now very clear that not only the metallocenes, the non-metallocenes with more cheaper and economic ligands are also possible for olefin polymerization. However, there is a disadvantage is that we have to sacrifice the stereoregularity. So, if you see that post-metallocenes are good for the high molecular weight polymers, for branching, inducing the branching, for LLDP polymers. However, if you want to get a pure tacticity or the specific tacticity, then it certainly it has a disadvantage, and in this case the metallocene based chiral catalyst, as example like C2 symmetry or C1 symmetry actually wins, and if you get like a syntactic polymers, then CS wins. So, this is very clear that how these catalysts are exciting, and why the different industry who are basically the polymer manufacturers have accepted these catalysts. In the next classes, we will discuss that how these catalysts have been transformed from lab to industry, because we know that we have discussed the homogeneous catalyst, but homogeneous catalyst had advantage and some disadvantage, mainly for the economic factor and purification factors and reusability factors. So that actually the industry personnel don't like. They all like the reusable, and which will be most cost economic method. So how we can transfer this catalyst to the heterogeneous catalyst, so transformation from the homogeneous to heterogeneous, that we shall discuss in the next class. Okay. So these are the references. You can consult the various books, and thank you very much, and see you in the next class.